Okay, so good evening, everyone. So I'll start with the binary phase diagram that we were discussing yesterday. So this is an example of a binary phase diagram. Which has copper and nickel. So a phase diagram, as I said earlier. So in this case, it has a composition on the x-axis and the temperature on the y-axis. So what it means that the pressure, that everything that we are assuming here, pressure is one atmospheric pressure. So pressure is fixed or constant. So what we are varying here, or what are the variables? So one is the composition. So what is the weight percent of nickel? So for example, this zero means your weight percent of nickel is zero and weight percent of copper is 100. So similarly, as we go along this x-axis, the weight percent of nickel increases and becomes 100, and the weight percent of copper decreases and becomes zero here. So this is what we mean the change in the composition. And temperature is of course this here, this 1085 degrees Celsius represents the melting point of copper, and on this axis 1455 degrees Celsius represents the melting point of nickel. So when you mix this copper and nickel, so they are very good, like they mix really well, they are really soluble in each other. So of course in the liquid phase there is doesn't matter, they will anyway mix, so there will be no segregation of nickel or copper atom, so to say. Now, as you cool down, so you will first meet a region. So, for example, a boundary which we call as a liquidus line. Okay. So, below this line, so you will have some solidification process will start, but you will have a mixture of two phases now. So, one is the liquid phase and one is the solid phase, which is the crystalline phase. So, alpha here represents the solid phase or crystalline phase, so which is normally FCC in this case. As you decrease the temperature further down, so you will meet another boundary. So this boundary is again a phase boundary, so which we call as a solidus line. And if you cross this solidus line, so you will only have the alpha phase that will exist. Okay, so in this case you will have only one phase, that is depending on the composition it will be one phase. For example, if I look at this point A, so it is a phase, alpha phase, 100% alpha, so there is nothing else. If I look at a point anywhere in this region, so it will be 100% a liquid phase, one single phase, 100% a liquid. So now the interesting part comes in between these two phase boundaries, because we have two different phases, that we have alpha, the solid, plus liquid. Now, if I look at one of the point, let's say B point, okay, so this is, and I drop a perpendicular line here, so I will know what is the composition of the total system. So alpha plus L. So alpha plus L consists of, uh, so this is about, let's say, 35 weight percent of nickel and 65 weight percent of copper. Okay, so this will be the total, the how much copper and how much nickel is there. But the amount of copper and amount of nickel that you have in the solid phase and liquid phase may be different. It will not be the same like 35 and 65, but it will be different. So how do we calculate that? So in order to calculate that, so what we do is we draw a line, a which we call as a isotherm or a tie line. Okay, so a tie line, something like this that we draw, so which is along the temperature axis. So this corresponds to the same temperature. So this line, everywhere the temperature is same. So we draw such a line, and then we look at where does it meet the liquidus and the solidus line. So let's say if it meets, so for example, this B point meets the liquidus line here. Now I drop a perpendicular to the x-axis. Now whatever is the composition here, so that will be the composition in the liquid, because this line corresponds to the liquid. So you have a transition from liquid to the solid. So this is a phase boundary that is representing the liquid line. So in this case, it will be about 32 point something nickel, and the rest will be copper. So which is different from the composition of the total system alpha plus. So similarly, if I look at how much copper or nickel I have, for example, in the solid phase, in alpha phase. So I will see where it meets this line, and then I will draw a perpendicular to the x-axis. Now that means I will have this about 42 or 43 weight percent will be nickel, and the rest will be copper. So this is how you can then identify individual composition of this in a two-phase system. Okay, so using this tie line. Now within this, so we have alpha plus L here. Okay, so which has C0 amount of nickel and 100 minus C0 of copper, but we don't know what is the percentage of alpha and what is the percentage of liquid, or what is the percentage of solid and what is the percentage of liquid in this phase. So it is definitely not 100% solid phase, it is also not 100% liquid phase. So how much percent is there? So that we can calculate using a rule called as a lever rule. So where you use this formula, so basically now you have to calculate what is the length of this line and what is the length of this line, and using that you can calculate the uh, percentage of liquid and solid phase. So if I want to calculate the liquid phase, the percentage WL, so weight percent, how much percent is liquid. So I will take the ratio of the total length of that line R plus S in the denominator, and in the numerator I'll take the length of this S on this side. So to find out the percentage of liquid. So you see how this now changes. Okay. So similarly, if I want to know what is the alpha, so I'll take the length of this line R and then divide by the total length. So if you substitute this RS value, so it will come out to be, so it will be like something like the concentration of alpha minus C0 divided by C alpha minus Cl. So similarly, the delta alpha, so W alpha will be C0 minus Cl, and by C alpha minus Cl. Okay, so if you substitute these numbers, so you will get what is the percentage of liquid or and percentage of solid. So in this case, one can do this calculation. So C0, I said 35 is the nickel and rest is copper. So you take the C alpha in this case is 42.5. So you subtract that. So this should be the sum actually. So this is also no, this is minus as well. So this is C alpha minus Cl. So then you calculate what is the total weight fraction of liquid, that is 68%. So the same calculation, so it will be showing, so definitely the rest will be your solid phase, that is 32%. So you can convert this liquid and solid to the volume fraction. Okay, so volume fraction, for that you need the density. You need to know the density of the solid as well as the density of the other phase. Okay, so if you know, so you can convert between the weight fraction to a volume fraction as well. Okay, so I also told that when we look at this solid and liquid phases, the microstructure is quite important. Why? Because microstructure can tell us like what will be the mechanical properties or any other properties for that matter. So that's why we need to know what is the microstructure during this phase transition process. So this is just like a phase transition is occurring. So how the microstructure develops, it is also interesting to know. So this figure shows you how the microstructure changes as we cool down from the liquid phase. So again, we start from 35 nickel. So this point, let's say we start, which is completely liquid, single phase, and then as you cool down, so we reach a temperature around 1260 or 1270, let's say. So B point we reach here on the liquidus line. So we have some nucleation of alpha phase. So alpha phase will be distributed very small amount, uh, negligible, almost very small. Majority will be your liquid phase. And then again you can use the lever rule to calculate what is the composition of nickel. So that will come out in the alpha phase. Nickel will be, so now again you draw a, so it will be about, you look, draw a line here and draw a perpendicular, so that will correspond to 46. So nickel will be 46 weight percent in this case. Now, if I come to this point, okay, so again we are cooling down. So we are cooling down along this composition. Okay, so the composition is fixed. So this is the C point, and here again you will have more and more alpha phase will develop, more solidification will happen. So liquid phase will decrease, solid phase will increase. So again, in order to calculate how much, what is the composition of nickel in alpha, again you draw this tie line, then you drop a perpendicular, so that will come about 40 weight percent. So what you can see is in the in the solid phase itself, during the cool down process, the in the alpha phase itself, the nickel composition is changing. So here it is 46, here it is 40. Then when you come here, so it will be, the microstructure would look something like this. Most of the alpha particle will be there, and the composition of the alpha phase will be more or less a little bit less than 35 weight percent nickel, but more or less close to that. So you'll have the exact composition that you want for this alloy. So you have 35 nickel, for example, at D and E. So you'll have almost 35. So at E exactly equal to 35 weight percent of nickel. So D it will be very close. So this shows that during the cool down process, even within the alpha phase, within the solid phase, the composition of nickel is decreasing. So that means uh, uh, so uh, more and more copper is getting introduced into the alpha phase, and that's why so nickel composition is decreasing. So why nickel composition is more? Because when you look at the melting points, so nickel has a higher melting point. So that means when it cools down, so it will freeze earlier than copper. So copper has a lower melting point, nickel has a higher melting point. So whenever we are cooling down, so we will first freeze nickel and then copper. So that means the liquid will always have more copper and the solid will always have more nickel in this case. And then only when you go to complete solidification, so the nickel composition will decrease and you will have 35%. So this is what we call as an equilibrium cooling process. It is a slow process. So what that means, that we are allowing for the equilibrium to get established. So liquid is getting, so when you reach, for example, this phase, okay, so alpha has been formed, and then you give enough time, sufficient time, so that the atoms they move, rearrange, okay, and then you get the solid phase. So similarly, when you go to C, for example, again you wait long enough so that the atoms they move, they rearrange, Okay, so you give enough time to form this alpha equilibrium phase. But when we actually process materials, so we don't follow this equilibrium cooling, because if you do that, you sometimes have to wait forever. Because when we look at the diffusion process, diffusion is very slow, it is sluggish. Okay, so it's a slow process. So that means if you really want a perfect the equilibrium, so it will take forever. So rather, what we do is we to a non-equilibrium cooling. So most of the time it will be a rapid cooling or moderate to rapid cooling. So it will be a non-equilibrium cooling process. That means you don't allow the equilibrium to get established, and that is also going to affect your microstructure as well. So this is what actually happens in reality. So the previous case is a more ideal situation, but this is what doesn't happen in real scenarios. In real scenario, what you have is a non-equilibrium cooling, a rapid cooling. So that changes the microstructure completely. So how that changes, let's look at. So again, you are starting from this point A prime, so which is 35 weight percent nickel, so completely full nickel. Then you meet, come here, meet those liquidus line at B prime. So you have again the same thing, which was similar to your equilibrium case. Why? Because the diffusion process in liquid is faster. So that means to achieve, even if you are doing a rapid cooling, so because the diffusion is faster in liquid, so you can achieve near or close to equilibrium when you are in liquid phase. So that's why you still have the small alpha particles microstructure which we saw earlier. Now, when you cool down, okay, so you get to the C prime, okay. In case of an equilibrium case, we expect that you will be having a 40 weight percent of nickel, okay. So in case of an equilibrium cooling, but because you have a rapid cooling, so what happens? The so of course, so nickel, we have frozen nickel. Now copper has to move, diffuse, and reach so that the alpha phase will form. So alpha phase is always made up of copper plus nickel. So now copper is not frozen, is in the liquid state, and the nickel is frozen, and because it is now solid and we are not giving enough time, so now the amount of copper atom that could diffuse, for if we wait longer, for example, so that would not happen. So that means actually what will happen, the uh, composition of nickel will increase, so at this C point. So in a equilibrium case, it should have been 40, but what it would be, it will be higher, it will be 42. So it will come down here. So now again, when you go to D prime or D dash, so again the same thing happens. In an equilibrium case, you would have expected already 35 weight percent nickel, but it is not it will not happen because it is already has a 42 weight percent nickel. So that means again the diffusion will be slow. You are not giving enough time, so the nickel content will be higher. So it will be 38%. So what you are doing is basically in a non-equilibrium case, you are changing this solidus line. So in a equilibrium case, if it goes like this, so the solidus line will get modified because of the rapid cooling process. And in fact, you will get the exact composition when you reach somewhere this E prime. Okay, so not at D prime but E prime. So how then the structure, microstructure would look like? So at C prime, we said we have more nickel. Okay, so 42. So initially we have 46 nickel at this point. Here we have 42 weight percent nickel. So this is what this the circle around this red one shows. Then again, when you come down, so another circle forms which has 40% nickel, and then finally you have a 35% nickel. So what you have done is you have created a concentration gradient of nickel during the crystallization process, during the solidification process. So you have created a change in uh, concentration starting from the center, so which has the highest nickel concentration, and as you go radially outward, so the nickel concentration decreases, ultimately it becomes 35. And then in fact it will even go further down, because the shift or the change in the solidus line, so what you will get is 31. So in this case you are getting 31 nickel, weight percent nickel. So your idea was to get an alloy of copper nickel with 35% of nickel, but what, because of this faster cooling or non-equilibrium cooling, what you have generated is different alpha phases, and alpha phases with different nickel composition, which decreases gradually or radially outward. So that means the copper concentration will be the inverse of this. So copper concentration will be more on this outer radius, and it will decrease as you go further towards the nickel. Okay, so this is, you have created a very interesting microstructure. So this non-equilibrium cooling, what it does, so it shifts the solidus line. So the shift depends on the rate, how fast you are cooling down. So this will be, even it can drop even much faster somewhere here. So if you cool down much faster. So then what you created a microstructure, what is called as a cored structure. So this is a cored microstructure. So what it means, so you have created a radial concentration gradient. So radial concentration gradient starting from the center. So the nickel concentration decreases as you go radially outward. The copper concentration increases as you the copper concentration, let's say, also if you go outward, so the copper concentration increases, the nickel concentration decreases. Also what you we have done is something called as a segregation of the nickel at the center. So what it means, because of this gradient, so what we call have is, we have a more nickel at the center and less nickel on the outer radius. So what we call this is as a segregation of the nickel phase and the distribution. So copper has an increased concentration gradient away from the center. And particularly what you see here, so this concentration gradient will create some kind of grain boundary. Okay, and most of the copper will be seen at the grain boundary. Okay, so the grain boundaries will have the copper reach, and the center of the grain will be nickel reach. And if you use such an alloy which has a core microstructure, and if you, let's say, do a mechanical processing where it is exposed to some temperature, okay, so what will happen, that because the copper is has a low melting point, so it will melt first. And since copper is on the grain boundary, so the grain boundary will melt fast. It will first start melting because copper is there, which has a low melting point, but the core, the grain part will not melt. So what will happen now, the grains start moving easily, because the grain boundary will not block anything, so which acts like a boundary or a blockage. So it is now becomes liquid, so it makes everything flexible and the grains move. If grains move, so that will deteriorate your mechanical properties, so the mechanical degradation will happen very fast. So that's why what people normally do, something called as a homogenization. Okay, so what you do is, this code structure is homogenized by a heat treatment process, and normally this heat treatment you will do below the solidus line. So somewhere about, so in this case, let's say around 1100 or 1150 degrees Celsius. So you will not go above this solidus line. So you'll do a homogenization process, and in that process what you do is, you allow the copper atoms now to move and readjust this concentration gradient. So this is how you can then improve the mechanical properties. So that means when you do a mechanical processing and this material sees a high temperature, so it is not like only the grain boundary will melt. So if it melts, it will melt everywhere together. Okay. Okay, so if you look at the mechanical properties, as I said, so another interesting thing, so you when you vary the composition, so typically what is observed, so you in the beginning, so when you introduce nickel in small amount, so the tensile strength increases, so it becomes maximum around 40 weight percent of nickel and then decreases. So on the other hand side, the ductility will have a exactly opposite behavior. So it will decrease. So copper has the highest ductility. So it will decrease as you introduce nickel. So it will be lowest or minimum about again 68% of nickel, and then it will again increase. So again you see a correlation between the tensile strength and ductility. Okay, so now we will look at another interesting kind of a binary phase diagram. So this is called a binary eutectic system. Okay, so these are also very, there are many materials which or alloys which exhibit this binary eutectic system. So what happens here? So here again we will understand it using an example. So we have taken a system copper and silver. So copper and Ag. This is a phase diagram of copper and Ag. So now again on the x-axis what you see is the composition. So here in this extreme case copper composition is 100% because copper is written here, and Ag will have 0. So as we go along here, so the Ag or the silver concentration increases and becomes maximum 100% on the right hand side. Now again, what you see here, again temperature is on the x-axis, and when you go, let's say above 1100 degrees Celsius, so you see everything is in a liquid phase. So this is your liquid phase, complete liquid phase. Okay, so this is called as a, again that separates as you cool down. So you will have various phases right now. Okay, so you see various names. So alpha, your alpha plus L, beta, beta plus L. So very different new phases appear. So in fact, you have now two different kinds of solids, so alpha and beta. So alpha is basically either it will be 100% copper, that will be you call as a alpha, or it will be copper rich phase. So normally that what you say as a alpha phase. So there will be small amount of silver that is introduced here, uh, a solid solution of copper and silver that you will call alpha. So similarly, beta will be either 100% silver or small amount of copper. So that means it will be rich in silver. So these are the two distinct solid phases you will get. Both are of course FCC in nature. So here you see a very interesting line. Okay, so this just a straight line that is at that maintains a particular temperature which is about 779 degrees Celsius. Okay, so this line B, so this is what we are calling at BEG. Okay, so this line is called as a eutectic line or a eutectic isotherm. So isotherm because the temperature is same, the constant everywhere. So this eutectic means it is easy to melt. So that comes from a Greek word eutectic, which means easy to melt. So what is the point B is actually? So if you look at point B, so this corresponds to 8 weight percent of silver. So if you draw a perpendicular line, it will correspond to 8 weight percent silver. So that means I can get a solid solution of copper plus silver only up to 8 weight percent. So if I go beyond that, so I will segregate, so the silver will not anymore dissolve in copper, so to say, like water. So if you mix sugar, and if the sugar is more than certain amount, so then the sugar will not dissolve into water. Okay, so similarly here in this case, the solubility of silver will be 8 weight percent. So if you increase more than that, so it will segregate and it will form another phase, that is a beta phase. So similarly on this side, so I can introduce copper with a maximum solubility up to this G point, so which corresponds to 91.2 silver, what percent silver. So that means it corresponds to 8.8 weight percent copper. Okay, so I will have at G point, so maximum solubility of copper in silver is 8.8 weight percent. So if I add more copper, so then again they will segregate, so it will not form a solid solution. So you will have a beta. So only up to 8.8 weight percent will form a solid solution. So this is again when we are talking about alloy. So this is a substitutional uh, diffusion that has happened. Okay, and the other phase will segregate. So again, if you look at the liquid part, so when you cool down, so you have again a liquidus line. So you have two liquidus line here. Okay, so E to F and A to E. So which separates the liquid to a alpha plus L. So again a solid plus liquid phase. So here we have also another beta plus L. This is again a solid plus liquid phase. Now, when you cool it further down, so of course you will get a alpha plus beta phase, so two solid phases. So not one single alpha phase like we saw earlier, but you get two different phases, alpha plus beta, and which will happen below this eutectic line. Okay, so this eutectic line, the solidus line. So this is again there is a solidus line here, there is a solidus line here as well, so which separates your liquid beta plus liquid or alpha plus liquid to alpha phase, or alpha plus L to the alpha plus beta phase. So this is not, you don't call it a solidus line, but you call it a eutectic line. So then there is another interesting line, so which we call as a solvus line. So there is this B to C and G to H. So this is a solvus line. So why the name is solvus? Because here you are basically going from a solid to two different solids. So alpha to alpha plus beta. So similarly from beta to, so when you cross this boundary, so you go from solid to another two solids. Okay, so that's why it is called a
Sir,
solvus.
what is, excuse me, sir. Sir, what is the difference
Yes.
between alpha and beta?
Alpha is again, they both are solid phases. So alpha has copper, more copper, and less silver. Most likely, the maximum silver you can have here is up to 8 weight percent. So if you add more silver, so it will just remain like silver. So it will not really form a solid solution. It will not be an alloy form. Okay. So similarly, beta is again a solid. It is also if it is an alloy, so it will only can hold about 8.8 weight percent of copper. So this is an alloy of silver. So beta will be always will correspond to a silver rich phase. Rich means there is more silver, and alpha will correspond to a copper rich phase. That means you have more copper. So whenever we see here alpha plus beta, okay, so you will have uh, so let's say if I look at this 40, let's say this point, okay, so I will have in the system, I will have an FCC a phase which has 40 weight. So what we are saying, we have 40 weight percent silver in 60 weight percent of copper. But if I look at a region as an alloy, so it is not one alloy. Like earlier, we have only one alloy, alpha. So copper and nickel. So they completely mix. So you don't have to worry about different phases. So this is one alpha, one single phase FCC. But here, alpha is one phase and beta is another phase. And alpha will have more copper, beta will have more silver. Okay, so this interesting point is this E, point E. So what you can see here, this point E is called as a eutectic point. And what this represents here, this point, so here you can see you have a liquid phase and you have solid phase that are coexist. So two solid phase, alpha plus beta. So if I go below this point, so I'll have alpha plus beta, and above it will be completely liquid. So this is called a eutectic point or a eutectic reaction. Okay, so this is interesting. Why? Because I have, so earlier when I'm going through a solidification process, let's say if I go through a solidification process here, so I'll go from liquid to alpha plus liquid and then alpha plus beta. So I'll go into solid, then solid plus liquid, then liquid. But here I go from solid to liquid like in a normal phase transition that you have seen when you go from a single metal. So if I take, for example, only copper, so copper will be solid and then it will melt and go to liquid copper. It will never happen that you have some copper solid plus liquid copper and then it will go to completely liquid phase. So as this melting will happen at a constant temperature, and it will immediately all the solid will convert into the liquid. So similarly when I look at ice, when it converts to water, so a conversion from solid to a liquid phase. Okay, so this is, this point eutectic point represents, and it happens only for this point in this case, which corresponds to a particular composition. So this composition is a eutectic composition which corresponds to a 71.9 weight percent of silver. So the rest is copper, 71.9 weight percent silver. So this is a fixed point in the phase diagram. So you cannot really change it by doing a rapid cooling or a fast cooling or any cooling you do. So this point will never going to change. So the eutectic point and the eutectic temperature will be always fixed. So this is why what you call it, this point E is a invariant point. So it is a invariant reaction. So there will be no variation. Doesn't matter how you do the cooling process. So in that, at that point, so you start with the liquid. So if you cool down, you will get alpha and beta. Okay, so two phases. So similarly, if you heat it, go the other way around, so it will directly convert to liquid. So there will be no existence of some alpha plus L plus alpha beta plus L or nothing like that. And that corresponds to this particular concentration, 71.9 weight percent, which then will correspond to the alpha phase where you have 8 weight percent silver, and the beta phase where you will have 91.2 weight percent silver. Okay, so these are the two phases you will get. So this kind of eutectic system also exists in other cases. So this is another very famous example of this phase diagram. So this is lead and tin. Okay, so lead and tin exactly exhibits a similar kind of phase diagram, eutectic phase diagram. So we call it the binary eutectic system. So again you have alpha phase, liquid. So here what you see, the temperature is really small, so about 183 degree. So this eutectic line is at 183 degree Celsius. So earlier it was like 799. So the temperature is different, but the way they behave is very similar. So the eutectic composition is 61.9. So this is a 61.9 weight percent tin will convert to 18.3 weight percent tin, and a beta phase which has 97.8 weight percent tin. Okay, so two different phases. So this alpha and beta again two different phases which are FCC in nature. And when you have this composition, so again when you heat, so this composition will directly melt or go into a liquid phase. So what is so nice thing about this? So the good thing is this lead and tin is used. This alloy is used for soldering. So if you have done any electrical soldering, you might have seen like some wire is used. Okay, so for soldering, so that wire is nothing but this lead and tin alloy. And normally you use a composition close to the 60 weight percent of tin. So you use 60 weight percent of tin and around 40 weight percent of lead. So when you do that, so you are close to the eutectic point, eutectic composition. So that means if I apply 183 degrees Celsius, so I'll easily melt that, and then I can use it for soldering purpose. So again, let's look at the microstructure, how it evolves in this case. So this is again the lead and tin alloy system. So if I start cooling down from here, okay, a composition close to this C1, which is very small, so about 2 weight percent or less than 2 weight percent. So you start with complete liquid. Then when you reach the liquidus line, so you'll have some alpha phase. Then as you go to the solidus line, so you'll have more and more alpha phases. And then when you go to C, so you'll have only alpha phase. Okay, so this will happen if the composition is a very small amount of tin is there in there. Now, if I move to the right, so now let's say I increase the composition. Okay, so in the melt or in the liquid, so I have, let's say, about 15 weight percent. So this corresponds to 15 weight percent of tin in the liquid phase. Now, when I cool down, so of course at here, so you'll cross the liquidus. So here, what you'll have again some liquid plus alpha phase, because that is what the phase diagram tells us. So you'll have alpha plus. Now, when you reach this point, okay, so you will have again only alpha phase. That is a single phase alpha. But if I come below now, this cross the solvus line, so what you will have at G, for example, so you have alpha plus a segregation will happen, so which will be your beta phase. Because your phase diagram says at point G, I will have two phases, alpha plus beta. I cannot have one single phase. So this is what you expect in as a microstructure in your sample. So similarly, if I move again further, go to the eutectic point. So as I said, so this is about 61.9 weight percent. So when you go below, so what you see is a lamellar phase. So like some alternate phase of alpha and beta will appear. Okay, so this is again a very interesting microstructure. So you, in this case, you have only few blue points, so which correspond to your beta phase, but here you have alternate alpha and beta. Okay, so they are again, so this is one grain. So if I look at one grain, so in each grain I have both alpha and beta phase, and they have similar orientation, crystal orientation, but they are really alternate to each other. So this is a very interesting microstructure. So the physical mechanism, how one can understand it, like in a eutectic growth, so you have a liquid. So now the solidification is happened from this end, so which progresses towards the right hand side. And in the process, what you have is alpha and beta, both phases are formed. So now whatever the lead Pb you have, so beta is rich in tin, alpha is rich in lead. So that means in the liquid, the lead atoms, so they will migrate or diffuse in this direction, and the tin will migrate in this direction. So they will go to the blue part, and the red lead will come to the red part. So that you will have the alpha and beta phase. This phase segregation will happen. You clearly see this two different phases, alternate phases forming in the same within the same grain. So this is actual a microscopic picture how this eutectic point, how the microstructure looks like. So you see this dark and white contrast, so that corresponds to the alpha and beta phases, two distinct phases. So which you can actually clearly see under a, this is you can see it under even a optical microscope or an electron microscope. So this is about 50 micrometer in size. So this is the length scale that we are looking at, and on a sample, the eutectic sample, so this is how the microstructure looks like. So this is one grain, separated by a grain boundary, and within the grain, so you see this lamellar structure with alternate alpha beta phase. So which uh, clearly matches with what you expect from the phase diagram. So that's why a phase diagram is an important tool, that if you know the phase diagram of an alloy, so then you can actually control what microstructure you want. Okay, so you can decide, okay, so I know the phase diagram, so now with what composition I should start so that I will get this kind of microstructure. So this is again a very interesting aspect here. So again, if I, instead of going through the eutectic point, so if I go a little bit to the left, now start a composition with this 40 weight percent of teen from the liquid phase. So what I will get? I will get first again some precipitation of alpha and the liquid. As I go further down, so the alpha phase will increase. But as soon as I go below, in cross this eutectic point, so I'm not crossing it exactly at the eutectic point, but another point. So I'm crossing the eutectic line at another point. So what you get eutectic structure plus some primary alpha. So similarly, if I do a cool down from here, I'll get a eutectic structure plus a primary beta. Okay, so this is what you will get. So this again is a kind of an interesting microstructure you can create uh, by just deciding what the initial composition, liquid composition from which I want to cool down. So this is again represents a microscopic picture of how, so you see a eutectic, this lamellar alpha beta phase plus the primary alpha phase. So which is like these big grains that you see here, so that corresponds to this primary alpha phase, and the lamellar pattern correspond to the eutectic microstructure. So again, it matches with what you expect from the phase diagram. So that's why phase diagram is very important when we want to make or design some alloy. So there are other phase reactions can also happen. Like I said, eutectic reaction. So there is another reaction which we call as a eutectoid reaction. So this goes from a solid to another two solid. So this all these Greek letters always represent a solid. Okay, so in a phase diagram, so whenever you see a Greek letter, so you immediately know it represents your a solid phase. So this delta, a solid phase, go to another two solid phase, gamma plus epsilon here, for example. So then there is another type of reaction, peritectic reaction. So where it goes from a solid, one single phase solid, to another solid plus liquid. So that we have already seen, but it is not the same. So your alpha plus L goes to alpha, but in this case peritectic, so it will go to another phase, actually completely different phase. So epsilon, that goes to liquid plus delta. Okay, so these are different things which might occur in different phase diagrams. So you need to know this type of, so you have three types of reactions. So one is eutectic reaction. So eutectic means liquid directly goes to two solids. Okay, so alpha L goes to alpha plus beta. Eutectoid, solid goes to another solid, two different phases. Delta goes to gamma plus epsilon. Peritectic, your solid plus liquid goes to another form of solid phase. Okay, so these are the possible reactions. So this phase diagram construction is also quite interesting. So we'll not go into the detail, but only we will see one particular rule which we call as a Gibbs phase rule. Okay, so phase diagram is definitely, it is a thermodynamic process because there is an involvement of temperature and pressure. So we are in this case, let's say, keeping the pressure fixed and varying the temperature, and that is how we are changing the thermodynamic phase of the material from liquid to a solid with different phases, with different constituents, different composition, and so on. So now, can we use this phase diagram and understand, like in a system, how many phases will coexist in equilibrium in a given system? So this is given by a rule called as Gibbs phase rule. So which is simply stated like this: P plus F equal to C plus N. So what is P? So this is a very simple equation, okay, but it has very interesting. Uh, uh, so you'll get a lot more insight or understanding of the phase diagram from this Gibbs phase rule. So what is P here? So P stands for number of phases. So phases, as we defined earlier, so it will be a liquid phase or a solid phase. Even in a solid phase, there could be two different phases depending on the composition. So it could be a copper-rich phase, or a silver-rich phase, or a lead-rich phase, or a tin-rich phase. So alpha or beta. Okay, so these are two different phases. Then F stands for number of degrees of freedom. So this degrees of freedom means how many external variables are there so that we can change the composition or change, sorry, not to change the composition, but we can move in the phase diagram. So how many parameters are there? So typically there are three parameters, that is temperature, pressure and composition. So if you vary these three parameters, so you can move in the phase diagram, the phase space. So C corresponds to number of components. So this is simply just number of elements that are present or number of compounds. So if I am talking about a copper nickel, so whatever I have on the left hand side, this is one component. Whatever I have on the right side of the phase diagram, so I will have that is my component. So if I have more than, so I can have more than I can have one component, I can have more than one component, or I can have two, three, more number of components as well, depending on how many alloys. So if I am making a binary alloy, so most of the cases we are discussing binary, so you have two components, but you can also have three components, four components, or more. And n, this number of non-compositional variables. So one is of course the composition is a variable. So how many variable are there which are not composition, which does not represent the composition? Basically temperature and pressure. Okay. So we will use this phase rule to understand this copper and silver system. You can also use the Gibbs phase rule for a lead and tin system as well, because they are very similar. So in this case, what we say, when we look at the phase diagram, so we have a temperature versus composition. So that means we are assuming the pressure is constant, that is 1 atmospheric. Okay. So this n, what is n? N is the number of non-compositional variables. So n will be equal to 1. So because that is the only variable, that pressure is fixed. So what is C? C, the number of components, that is equal to 2. You have copper and silver. Simple. So two elements, so composition, C components are 2. So then what? The right hand side of this equation, so C plus n, 2 plus 1 equal to 3. That means this number of degrees of freedom F will be equal to 3 minus P. So let's consider a single phase region. So where we have single phase, let's say here alpha. So this is a single phase. Okay, or liquid, it is a single phase. So if I say it is a single phase region, so P is equal to 1. So P represents the phase. So that means the degrees of freedom, the number of variables is 2. So that means if I want to pinpoint or understand a point in this phase diagram, in this region, so I need two parameters. The number of degrees of freedom, I said 2. So that means I need two variables or two parameters to define or understand the phase system in this single phase region. So in this region or in the liquid region. So what are those parameters? I need both, like two coordinates, temperature and composition. So if I know this, so I can clearly identify this point in this region. Now consider this region. Okay, so I have two phases, alpha plus n. So this is P is equal to 2. So in that case, the number of degrees of freedom will be equal to 1. So what it means? Now, if I want to find any one the details about any point in this region, I only need one variable. I don't need